Hey everybody, welcome to today's lesson. Today we're going to be focusing more on our discussion on heat energy. And I wanted to start today off with a quick video, so let's go ahead and get started. All right, excellent. So today what we're going to be looking at is why did that balloon not pop? So let me go ahead and get rid of this and get to our notes sheet for today. So today we're going to be focusing on what is called specific heat capacity. I do want to go ahead and take a moment and just record those observations that we saw so that you do remember those if you ever go back and reread these notes. So in the video, we placed two balloons over the flame, okay, and the balloon with no water pops, okay, but the balloon that has water does not. Okay, excellent. I love doing this demonstration in class, and I have to say, I think the key must be using the candle. I sometimes try to use the Bunsen burner, and it results in a popped water balloon. It's very messy. But let's go ahead and jump in and talk a little bit about why it wouldn't pop. And so to start us off with this discussion, I do want to take a moment and just envision a really nice, beautiful, warm day at the beach. Now I'm talking one of those like August days. I don't even want to say nice warm days. I want to say hot days at the beach. Those days where you get to the beach and you are just sweating the instant that you get there. And so first and foremost, I want to talk a little bit about the transfer of heat, because remember, we've now defined heat as the transfer of energy. And there's no sunshine included in this picture, so I am going to go ahead and sketch one in there. But where does the heat flow occur in this image? Okay, heat always flows from hot to cold. And so if we're envisioning our heat transfer, all of the energy that is provided to the beach and to us as beachgoers comes from the sun. So the heat flows from the sun to the water, okay? And it also flows from the sun to the sand. Okay, so this is also heat flow. And so again, heat flows from the sun to the sand and the water. Now, I don't know if you are super familiar with going to the beach, if this is something that you guys do frequently. I know growing up in Rochester, New York, we didn't really go to the beach that often, but since I got married, my husband is from Long Island, and we do spend a lot of time at the beach in the summers. And so I have to say, this experience on day one of going to the beach, I was very surprised. So I get to the beach, and the first thing that I like to do when I get to the beach is just rip off my flip-flops. I hate walking in flip-flops or sandals on sand. It drives me nuts. But what do you think happens when you remove your sandals on a really hot day at the beach? Okay, it was instant burning on the bottoms of my feet. And so, unfortunately, right, how do I fix that burning on my feet? The first thing I had to do was run directly to the water, and the water was cool and refreshing. So on a very hot day at the beach, the sand is burning hot. However, the water is refreshing and cool. Okay, but both of them receive their heat, or they receive their energy from the same source, the sun. But what do we notice? We notice that the sand heats up or increases in temperature much more quickly than the water, which takes longer to heat up. Okay? And so this concept is known as the heat capacity. Sand and water have a different heat capacity. And so let's go ahead and define heat capacity. So actually, well, let's jot this down. So sand and water have different heat capacities. Okay? And so a heat capacity, okay, is how much energy is required, or I'm sorry, let's actually erase that. How much energy, okay, a substance will absorb to change 1 degree Celsius. So how much energy is needed in order for the substance to change 1 degree? And so sand has a very low heat capacity, and that's kind of hard to understand, but if you think about that, it requires sand very little energy to change 1 degree Celsius, whereas water has a very high heat capacity. Okay, and it takes water much more energy to change 1 degree Celsius. So it's a little bit backwards to say that sand has low but gets much warmer, and water has high but doesn't warm up as quickly. I understand that, but hopefully once we start to add units into this problem, this will make a little bit more sense. Okay, however, we are not done there. Okay, there's more to it than just talking about just heat capacity in general, because we are not always comparing equal parts of the substance, okay, or equal masses of the substance. So here I have a second situation, okay? We have the kiddie pool, or we have the lake. Now, again, growing up in Rochester, New York, I didn't really use kiddie pools too often. We actually have a lot of lakes up in Rochester or the Bay, and so I did spend most of my time swimming in the lake. However, which one of these is going to heat up faster? Do you think the kiddie pool heats up faster, or do you think the lake will heat up faster? Okay. And if you said that the kiddie pool heats up much faster, then you are absolutely correct, okay? The kiddie pool will heat up much faster. So when comparing two objects that have the same heat capacity, right? They're both made of water, okay? The mass plays a crucial role in the energy needed to change the substance 1 degree Celsius, right? Because if there's more of it, it's going to take it longer. It's going to take more heat energy in order to change that body of water 1 degree Celsius. And so heat capacity, while it is a useful piece of information, is not as useful as using what is called the specific heat capacity. And so our specific heat capacity is the amount of energy required to change 1 gram of a substance 1 degree Celsius, okay? So specific heat capacity is primarily what we're going to focus on using in this course. So I just wanted to lead us in with that understanding of heat capacity into specific heat capacity. Now, specific heat capacity is carries the units joules per gram degrees Celsius. So if you really read into this, it states this requires X amount of joules for every 1 gram to change 1 degree, okay? And so let's talk about relative heat capacities or specific heat capacities. And I'm actually going to pause my video for 1 second just to pull up some specific heat capacities so we can compare those values. Okay, sorry about that pause, everybody. So I just wanted to grab a couple of specific heat capacities just to kind of show you what I was talking about with heat capacity and talking about low versus high. So to give you 2 values of specific heat capacity, just to show you what this means, okay, water has a specific heat capacity of 4.18 joules per gram degrees Celsius, and that's going to be our heat capacity of water. And what that says is that for every 1 gram of water to change 1 degree Celsius, that water has to absorb 4.18 joules of energy, okay? So in order for it to change 1 degree, for every 1 gram to change 1 degree, it needs to require 4.18 joules per gram degree Celsius, okay? Now, with water, I don't know if you've noticed this, but I feel like when I'm starving and all I want is just like a nice bowl of pasta and I put that water on to boil, it takes forever, okay? And that's because of that very high specific heat capacity. That water has to absorb a lot of energy in order to start to change temperature. However, I don't know if you've ever heated, let's say, a metal, and you'll notice how hot metal gets very quickly. And so the specific heat capacity, just to give you a general idea of that, of aluminum, right, which is what a lot of cookware is made of, or if you've ever used aluminum foil to help you reheat things, aluminum foil has a specific heat capacity of 0.900 joules per gram degrees Celsius. And what that means is that in order for every 1 gram to change 1 degree, it only needs to absorb 0.900 joules of energy. So they are required to absorb very different amounts of energy in order to undergo the same change. Aluminum only needs 0.9 joules of energy, where water requires 4.18. So it takes water a lot longer to heat than it does aluminum foil or aluminum. Okay, now specific heat capacity, when we're talking about this, we're always talking about a temperature change, right? We're talking about it literally undergoing a change to change temperature. This is based on temperature change. Now, the equations for heat that we've talked about so far, heat of fusion and heat of vaporization, are not talking about temperature change, right? During those portions or during that calculation, we're talking about how much energy is required in order to overcome the intermolecular forces or to change the phase of a substance. However, when we're talking about using specific heat capacity, we're talking about changing temperature. How much energy does it require to change a temperature? And so our equation needs to change. The equation that we're going to use is Q equals mc delta T. Okay, Q again represents our heat energy. M again represents mass. C is our constant, which is the specific heat capacity, which again is a constant. It will have to be provided for you, or if you remember from our lesson, you might be able to find that on the reference table. Okay, and delta T represents actually, let me change the color here. Delta T represents our change in temperature. That delta, the triangle, represents change. And we actually use the equation TF minus TI. That's final minus initial temperatures, okay? And so our new equation, Q equals mc delta T, will help us calculate the change or the heat associated with the change in temperature now, as opposed to a phase change. So let's go ahead and take a look at one practice problem together, and we'll save the other ones for class tomorrow. So here we have a practice problem, okay, how much energy, so that's Q, so we're looking for Q, would be absorbed when a 15-gram sample, that's our mass, of water is heated from 10, that's our initial temperature, to 30, that's our final temperature. Show all work. Perfect. So we know we see two different temperatures, so we know we have to use Q equals mc delta T. Q is our unknown. Our mass is 15 grams. Okay, our C, our specific heat capacity, is a constant. And we can actually find that on a reference table B, but we are talking about water, and so it's 4.18 joules per gram degrees Celsius. And then our delta T, which remember we said is TF minus TI. So TF is 30 degrees minus 10 degrees, giving us 20 degrees Celsius. So we set this up and we get Q equals 15 grams times 4.18 joules per gram degrees Celsius times 20 degrees Celsius, and we can solve from there. So we plug this all into our calculator and we get 15 times 4.18 times 20, which is going to give us 1,254 joules of energy. Okay. All right, everybody. Thank you so much for tuning in, and I will see you guys in class tomorrow. Have a great rest of your day.